So types of coding, channel codes. So block codes. First is block codes and second one is convolutional codes. So let's say about block codes. So the information sequence is partitioned into message blocks of k info bits each. That is represented by u. U is nothing but the message block which is having k bits starting from u0 to u of k minus 1. So the encoder will map the codes of k bit info bits u to the n bit code word called v. So u is having 0 to k minus 1 and v is having 0 to n minus 1, means n bit v, u bit k bit u. So k bit u is mapped to n bit v. As encoder is not having any memory, so it is a memoryless channel, memoryless element. So it directly maps each and every bit of u to v. Next, code rate. Code rate is nothing but r is equal to k by n. So where n minus k is nothing but redundant bits which we are going to add. The set of 2 power k code words of length n is called as binary n comma k code words. So we are going to have with length n, as we have u is equal to as we have v is equal to 0 to n minus 1, means n bits in v, we can form 2 power k code words using that. So code word sequence generally will take it as in practical we will take it as binary, but generally it is of non-binary. Let me take an example where k is equal to 3 and n is equal to 6. It is nothing but the code block length is equal to 6 and we are using the repetition codes is equal to 1 by 2, which is nothing but k by n, right? So that is 1 by 2. So each and every bit has to be represented with 2 letters. So let me take the message signal as 000, 100 and so on, and each and every bit has been represented with 2 bits there. So it may be with error, so no issues with that. So convolution codes means it is a memory based code, so which is based on the n bit encoder output at a particular time depends upon the k bit info signals, and at the same time it depends upon the m previous bits also. So it is represented by nkm, where n is the length of the sequence and k is nothing but present values and m is nothing but previous values. So n and k both are less than, whenever we are comparing to the codes nk, these nk will be less in values. So we'll take an example of the convolution codes where ul and ul minus 1 is past 1 value of u and past 2 value of u is called as ul minus 2. So vi is not having the value of ul minus 2 and ul, and v1 is having both u1, all the values of u, like u and ul minus 1 and ul minus 2. So this is the syntax which we will going to follow. And next one is decoding strategies. Decoding strategies, we will getting u info sequence based on r. Generally, we will get a u estimate. We after receiving r, we are going to estimate what is being transmitted. That is u estimate. So we will get this u estimate from v. By mapping v to u, we are going to get the value which has been transmitted. Generally, after getting v from r, we will get v, and by mapping v to u, we will get the exact code word which is nothing but the information sequence which have been sent. So here the average probability of error is nothing but the probability error is nothing but when av estimate is not equal to v, then it is called error. So we can represent the probability of summation of all the probabilities of error given r into probability of r. So that can be represented, error is nothing but v bar, v estimate not equal to v, right? So we can represent there, and we need to choose v bar, v estimate in such a way that the probability of error should be minimized for each and every value of r. So we need to minimize the error, means we need to maximize the correct information that is being given here. V not equal to v, minimization is nothing but maximization of p probability of v estimate is equal to v given r. So for each and every r, but we will be getting what we get an output of probability of v by r, not we get probability of r given v, I guess, right? So for each and every r, probability of v by r is equal to probability of r by v into probability of v given divided by p of r. So in order to increase this, we need to increase this, or this and this is directly proportional using Bayes theorem or something else. So for every v, we need to choose the maximization of v by r. So v by r is directly depending upon r by v. So here we use map, that is nothing but maximum a posteriori probability decoder to choose vi that maximize probability of v by r. So all the code words are likely, equally likely. So we can say something like p of v by r is equal to probability of r by v. So in this case we will use ml, that maximum likelihood decoder, which chooses v estimate of v such that probability of r by v is maximum. For discrete memoryless channel DMC, that is received signal will be correspondent to the, is directly proportional to the transmitter signal. So whatever the transmitter signal is there, that will be directly, it is getting mapped to the received symbols. So we don't have any memory to make use of the previous bits, so it directly depends upon the information which is get received at the particular time. So p probability of r by v is nothing but product of probabilities of ri by vi, so current informations. So generally maximizing this part is nothing but using logarithm, maximizing along with logarithm, because log x is nothing but the monotonically increasing function of x. So maximizing p of r by v is nothing but maximizing log of p of r by v. So example of ml rule for BAC: for a code word of length n transmitted by BAC channel with a crossover probability p, then we use ML decoder rule. How do we use ML decoder rules? Generally, we will select the Hamming distance d is equal d of RV. Between R and V, it is nothing but Hamming distance we already know. So whatever the received signal and whatever the estimated signal, what is the difference between both the things? Means what are the what are the error bits? So what is the change in each and every bit of the R and V? So that is the whole Hamming distance. So increasing the log of PR R by V is nothing but log, this we have formula, this is a formula. So Hamming distance into log of P divided by 1 minus P plus N into log of 1 minus P. Generally we can derive something like Hamming distance into correct probability, Hamming distance in plus, sorry, minus Hamming distance into 1 minus wrong probability plus N into log of 1 minus P. So log of p by p minus 1 minus p less than 0 for all probability of less than, for all the p 1 less than 1 by 2, and n log 1 minus p is a constant. So for each r, choose estimate v as a code word v to minimize the distance, Hamming distance. So this is linear block codes. Linear block codes can be defined as like this, where n comma k are the linear code blocks can be defined by using k by n generator matrix, where generator matrix is having 0 to k minus 1 n minus 1, which is nothing but n comma k linear block. So we can say something like there is a possibility of 2 power k binary code words formed by using the combinations of the rows of the G. So for each binary sequence, we use binary info sequence is nothing but U. Info sequence is U, and the binary code word is given by V. So we have a relation between V and U as V is equal to U into G. Okay, we can define over there. So whatever the plus we are using here, U naught into G naught, something like that, no? So the modulo 2 addition is used, and we have modulo 2 addition as 0, 0 plus 0 is nothing but 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, and 1 plus 1 is equal to 0 is the main point which we need to notate. So here V1 plus V2 is a code word. Whenever V1 is a code word and V2 is a code word, then their addition is also a code word. This is a point which is given in the GATE exam also. So things to be noted here. So all 0 vectors, 0 is nothing but 0, 0, 0, 0, 0. That is a 0 vector, is it, no? So every 0 vector is also, all 0 vector is also a code word in the every linear code. So an n comma k linear code block is a k dimensional subspace of vector space Vn. So out of Vn, the n comma k is nothing but a k dimensional vector space, subspace of the vector space Vn for all the binary n tuples. So this can be defined here very clearly. K is equal to 3 and n is equal to 6. So k is equal to 3 means we have information bits as u0, u1, u2. So code words means n is equal to 6. So we are going to have the outputs as v0 to v5. Generally they are represented with some format. So let it to be. So we need to define the how the v is related to u. By observing the format, we can able to identify that v0 is equal to u1 plus u2, and v1 is equal to u1 plus u0 plus u2, and so on. And finally we can able to observe that v3, v4 are directly proportional to u0, u1 and u2. So finally we could able to get their u into g. So we can observe that and we can make the format of the matrix and we can find. So u1 plus u2, v0 is equal to u1 plus u2. So we need to please, so 1 1 over here, and v1 is equal to u0 plus u2. So u0 plus u2. As in the same way, we need to fill all the things, and finally we could able to observe that the last three bits are nothing but 3 by 3 matrix, identical matrix. So after making this happen, generally what do you do? So for u is equal to 101, let me take u is equal to 101, this part we need to get this code word, whether it is getting or not we need to test. So 101, and using the generator we are going to get this, and which is similar to the part here. So we can make a tally of that and we could able to get that. So this is how we will find, given a u we can find v, and given a v we can find u, right? And general and n comma k linear block is an systematic form, which is nothing but g can be represented into p comma I, where p comma v is equal to u comma g, where code word is nothing but message signal plus parity bed checker, right? Parity check part. And g is nothing but p comma I, we already said. So p is nothing but which is having its size from k minus 1 to k into n minus k, right? So it is nothing, k minus 1 is nothing but it start from 0 0, no? So it is having its length as it is wrongly given here. It is nothing but k to k by n minus k, and I is nothing but k by k, right? So linear code block is having n minus k by n parity check bit. Okay, generally if you want to prove something like v as a code word, we need to follow this condition. If we want to say v as a code word, then it should possess v into h transpose is equal to 0. If this satisfies, then only we could say that there is no error. At the same time, we could say that v is a code word. So let me take an example where consider say 1 comma 4 as a linear systematic code given as a generator matrix, and we are going to do the same thing which we have did till now. So v naught is equal to, we are making the assumption, we are making the things very very clear, like making the arrangements of this. By putting here also we can make this done. So after clearing that, we are using modulo 2 addition, where we need to make it 0, right? What we need to specify the equations. So actually what we have here, so v naught is equal to u naught, u2 and u3. So u naught plus u naught will gives us 0. So v naught plus v3, and u2 has to be get cancelled with v5. So v naught plus v3 and v5 plus v6 is equal to 0. So this is the syntax which we are going to follow here. So in order to make the whole sentence 0, we need to make add with the other thing. Let me take for v2. v2 is having u1. So where is u1? So v4. v2 plus v4 and v5 and v6 is equal to 0. v2, v4, v5, v6 is equal to 0. So now you got this, right? So v is equal to, so we will be writing v into h matrix is equal to 0. So that has to be followed. So finally, G2 parity matrix is formed. Given a G matrix, we are going to get the parity matrix here, right? The first is an identical matrix, and the other one is a P matrix. And this is only possible if and only if the given generated matrix is of systematic code. And generally, the systematic code is a very bad code because it has poor performance, because the low density parity check matrix is not defined in the form of systematic form. But we are going to use all the systematic forms in order to make the same thing simpler. But generally, we have non-systematic codes only, so we need to make that study of it. So generally G is used for encoding and H is used at the decoding section. So syndrome and error detection. Syndrome has let v is equal to v naught to v n minus 1, which is nothing but the code word from the binary n comma k linear block codes with generated matrix G and parity check matrix H. So let me assume something like will define directly. So what are these? R is given, and which is nothing but v plus e, which is nothing but having modulo 2 addition, and e is a generated pattern, and ei is equal to 1 when it is not equal to 0. When the received and transmitted is not equal to not when they are not equal, then we will be getting error. So when they are equal, we won't be getting 0, we won't be getting error. So that is represented by 0. So if you want to say something like R contains error, so that is called as error detection. And at what place the error is, that is called error correction. And given a if no error, we, if we want to prove something, like if you want to detect whether there is an error or not, we need to check with this. So v into h transpose is equal to 0. This means v is a code word and no error. So as in the same way, we can use the syndrome here. S is equal to r into h transpose. So if r into h transpose is equal to 0, then we can say r is a code word. At the same time, there is no error. And if r into h transpose is equal to 0, if it is not equal to 0, then we can say that r is not a code word and there are transmission errors. So remark is nothing but, if r is a code word, if r is a code word other than the actual transmitted code word, then there are unhidden, like undetectable error occurs. So this happens whenever the error pattern is non-zero code word. Okay, so S is equal to S is equal to R into H transpose. But R we already know, V plus E. So by substituting that, we can able to get that V into H transpose plus E into H transpose, where V into H transpose is nothing but 0. We already know. So S is a syndrome which is purely depending upon E into H transpose. So consider H comma 4 a linear code with parity check matrix, where H is nothing but this pattern which I and parity, and R is nothing but S and syndrome we need to find. So syndrome is nothing but R into H transpose. We can make the use of it. This and this is there. So we got this, and which is not equal to 0. So error is detected. So already error is detected. We need to correct it. So we got to know that error is there. So error detection is done. So if we want to avail for the error correction, we need to use the same pattern, and we need to make the arrangements in such a way that Sj is nothing but error into H transpose, right? H transpose is nothing but this part. So we need to make that things clear. And we have n minus k equations with in n unknowns, that is error we don't know, right? So that unknowns, and a decoder must solve all these equations for the to get the estimation of error. So decoding of linear workloads. So in this we are going to have the R has n possibility. Generally r has n 2 power n possibility regardless of whatever the v is transmitted. So any decoding scheme we can use at the receiver to make the partition of 2 power n code blocks, possible received vectors, into 2 power k disjoint subvectors, nothing but d1 to dk. So that we can make something like such that vi is contained in the subset. So we want to make 2 power n possible transmitted vectors, getting partition in 2 power disjoint vectors, so that we can make use of vi, so that vi should be in one of the subsets. So we need to make these arrangements. So for that case, we want to take vi is equal to all zero vector and remaining parts as it is, so that 2 power k code words will be there in n comma k linear code word. And we need to make this arrangement where we this arrangement, first row all is v values, like we are vi is equal v1 is equal to 0 and other code words v2 v3 v2 up to v power 2k. So we divided that code word into 2 power k, right? So we need to define that. So then we are going to make the error values like 2 e2 e3 e4 up to e power 2 e power e2 power n minus k. Okay, so these are the error vectors. So this first, each and every row is called as coset, and each and first element of the coset is called as coset leader. So the first element in the coset leader, and we need to make sure that every this e2 and v1 should have minimum distance Hamming distance, and e3 and v every bit followed by v1 should have minimum error Hamming distance. So we need to write in this form, and the successive next values of the coset e2 then this element has to be designed in such a way that e2 must be added with the code word and e2 must be added with the v3. So this is the pattern by which we are making this happen, and this has to be done till we end up with all the vk and ek values. So ej values, there are 2 power k possibilities through which 2 power k possible solutions for the syndrome, and only one represents a true error pattern. So in order to reduce the probability of error, most of the probable error patterns are satisfies the above equation is chosen. So whatever the exact probable error pattern which satisfies the syndrome equation, we need to choose that as a true error vector. So let me take an example of BSc. First first we'll recall for BSc ML decode chooses v power v estimate as a code word, which is used to decrease the Hamming rate, right, of the error pattern. So H is nothing but given, and R is given, V is given, and S is given, and by S we can calculate as R into H power transpose, which is nothing but 111, so that we can found like if it is 0 there is no error, it is not equal to 0, so there we can find something like there is an error. So we are making these arrangements, 1 is equal to E0, E3, E5, E6. How we are making this is nothing but we are going to have E into H transpose, right? So E is nothing but E0, E1, E2, and we are making the things very clear, like this multiplied with EH transpose. So we are going to get, so E0 plus first one, E0 plus E3 plus E5 plus E7, right? Or E5 plus E6. This is something which we can define for three rows. We got three syndrome values. Then by which we can get a 2 power 4, means we have what 4 is nothing but, yes, parity bits are 4, right? So depending on the parity bits, that is k values, we are going to have 2 power 4 solutions for that. So after getting all the possible solutions, we need to define one particular error as a one particular error solution, one particular solution to get the error pattern. So we are taking one each and every time, we will be taking one and adding with the v. So at once and only once we will be getting a single digit error, so that is a true error pattern which we can decide it. So this is the last part. So we can have 2 power k elements of the cosets having the same syndrome as the coset leader have. So since S is equal to, we already defined this part. So 2 power k elements of the cosets are 2 power k solutions of the syndrome, we already knew. So we are going to define the dj as vj. So this is the jth solution, right? So this is all not expected, so we'll discuss about this later.